Yeah, thank you for also having me for this talk. And I want to take the opportunity to introduce the Materials Commons for You project, which of course should deal with a lot of the challenges we discussed already, and also try to summarize what potential solutions we will have developed in this project. I mean, a very quick history, so it's not really important on the detail, but it is a long history to go through to what we now call Materials Commons, starting with the Materials Manifesto and then shaped through the IMI 2030. And finally, a part of a SRIA and of a funding call last year. And now the winning consortium is able to launch the project just in a few days on Monday. So this is the timeline. And it is actually the call of the Commission to kind of clean up with the separated landscape of European research data infrastructure, which is of course mostly driven by national efforts like in Germany, NFDI, Material Digital, but also in other countries like CAPEX in DK, and also some already European level initiatives, Materials Cloud, or in France, of course, very popular, yeah, Diadem and the Diamond digital infrastructure of Diadem. Yeah, fitting this mission, it also integrates, yeah, not all relevant partners, but many relevant partners across Europe. And we also have associated partners and collaborators also from industry. Despite all core partners are academic, of course, we need to aim for industrial adoption. That's for sure. Yeah, so what is the mission now? So that's not very readable, but the idea is that most of the stuff you need as a digital materials researcher is somewhere present. But we, of course, need physical infrastructure that can deal with experiments. We need compute infrastructure on the other hand, and we need data, I mean, existing data, and we want to store, as we heard, newly created data in repositories. But the question is, if I have a use case, I have a research topic, how do I connect existing physical infrastructure, computation infrastructure, and data infrastructure to a workflow that actually implements my research? And this is not easy and often too complex for a single project, in particular too complex for a single researcher. So that's what the Materials Commons try to be, is this semantic core in the middle that makes the fabric that connects these infrastructures actually happen. And of course, it's not, yeah, it could not be a centralized platform where everybody needs to go and there's a single owner. But of course, as industry finds as answer for their data spaces, we need to have a federated system, and everybody can provide something and can get something back from the federated system. So you could have data, you could have services, you can have physical infrastructure as we provide in a federated network. And it should be able that you, on the one hand, can really benefit from what is existing, and on the other hand, you also may shifting towards actual business models by providing services that are maybe even paid, especially for us as a physical service. You need to pay something, but it may not. You may just reuse existing physical infrastructure. And even if it's data-driven but high computational, you may offer the services also not free, but you first need to advertise that they are available, and you want to make sure that the data flow from and to such offers is seamlessly. Yeah, so to summarize, the mission is to create this pioneered federated digital infrastructure following the industrial blueprints, but adapted for the materials research domain. Of course, this means fair data actually implemented, not just claimed. That's the, yeah, following up on our discussion. And it also covers all elements of research materials, so it's both experimental, computational, self-driving labs, workflows, and AI, and so on. yeah, we have 3 domains which cover roughly the core building blocks, first starting with semantic interoperability. I mean, there's nothing to explain much here, but the main point is that it's not just saying, let's create an ontology. Of course not, because we are experienced. That means we say there are existing ontologies on every granularity, top level, mid level, even domain, of course. But the question is not so much, is there ontology missing, but actually we need certain patterns to represent information of interest for domain researchers. And a researcher does not ask, is there a chemical engineering ontology? Is there a instrumentation ontology? Is there characterization ontology? They ask for, is there a pattern to store my experimental data? Like input, output, process steps, characterization results. And if yes, I want just to fill in my data somehow, and I do not really care much which ontology is mapped to which, but I want to have a template kind of. And this is what this area should also provide as an answer, not just as a formal specification of such a template, but as an actionable template that can be manually, visually accessed, but also, of course, could be machine actionable or driven even by LLMs. Yeah, workflows is also a popular problem to process data, to run workflows experiments in a interoperable way, and also understand what is actually was happening and which asset was consumed, was produced by a workflow. This is the second domain. And the last domain is more cross-enabling, dealing with this data space topics of connecting, interoperability, and protocols. Yeah, so yeah, to now deep dive into some of the challenges I want to point out here, because it makes is a good fit also for MatCHMaker, is the current limitation. So that's some infographics greatly created from AI, from our concepts. Yeah, of course, there is no coherent practices to annotate data. We have maybe different silos of metadata that are just disconnected. Definitely industry uses different approaches or also invented already better approaches. And if you now want to say, I use a software to make data-driven research, you may end with 20 tools, different tools that all have a very dedicated purpose, but not really covering your full research cycle in a single application. Yeah, that means the solutions we provide are, of course, to have a foundation. I mean, there's a lot of work done. It's more like inventorizing vocabularies, taxonomies, ontologies, and then deriving these patterns, how to store this kind of information, how to document a process provenance in a computational way, how to do it in a physical way, how to store observations, measurements to really make them interoperable. And these patterns are, of course, then flexible enough to shape specific data containers that you can ship. And somebody that receives this container can say, okay, I completely understand where the sample comes from, how it was characterized, and what are the results from the sample. And also here we can take a look at industry, which defines as an administration shell as such a container that contains all relevant information about the product. So why not think similar for a research product and have a container for this as well? Yeah, and I mean, of course, we are aware of knowledge graphs as a connecting fabric. So even if you have a file system-based container, it should be still a knowledge graph, kind of a exported piece of a knowledge graph, but you can run it locally, and you have a local knowledge graph. You can ask questions to it, but you can reconnect it to a larger knowledge graph, and you can re-separate from a larger knowledge graph. So the concept of a knowledge graph is really powerful and must not die just because we move to a file system, because the file system is a legacy system that is still very relevant. Yeah, and also to have a cross-connecting angle here, of course, in MatCHMaker, also effort was taken to find additional domain ontologies and certain patterns for the use cases. So why not, handing them over to Materials Commons as inventory for others to reuse. Okay, and the final layer is, of course, we all know a knowledge graph is nice and ontologies are powerful, but they are nothing to end users if they are not wrapped in a nice package, in a nice surface, a user interface. So we need to have this building blocks to build services. It could be UI driven or it could be automated AI driven, but all these fundamental questions, how to enable searching a knowledge graph, how to connect the LLM to it, how to make a graphical representation of your knowledge, of your data, how to edit data on a knowledge graph without making it on bar RDF, and then making advanced services like integration data, visualizing, plotting data. It's building blocks that every project reinvents because they need. We also have seen a platform for MatCHMaker. You need to render a graph. You need to have a tree-like structure of your project data. So you reinvent also these components to enable users to interact with the data. So why not use a common library? So we skip building the building blocks, but just building specialized services on top of it, which makes much more sense and will enable us to build such a research data platform in the very first begin of a project and not in the very end, as we also had as a challenge. Yeah, particular focus also from our own research is that we, in the end, need to have a representation of information that somehow makes sense for a robot in the lab, AI in the cloud, and a human operator in between. And this open semantic lab infrastructure has its roots. Also, its core concept is, of course, knowledge graph driven, and then we say we just put everything what we have in a knowledge graph. And if we have a knowledge graph, we can build interfaces to various other ecosystems. So RDF, DCAT is RDF, so it can be part of a knowledge graph or it can be derived from a knowledge graph. So we can connect them already to industry, which also says, let's put a DCAT catalog. We can also schematize the knowledge graph, which connects us to the asset administration shell. We should, of course, reuse proper ontology engineering, and we should have interfaces to, run complex queries, reasoning, and also feed into other systems that maybe not even understand RDF, but still are important. So like this button that pushes something to Zenodo, maybe just cut something off the knowledge graph, leaving, of course, reference RIs behind, but putting this piece in Zenodo, and then you're done. And you have something done good for fair data. So how could it work? I mean, this is my personal challenge and with my team. And we worked a lot about standards on interoperability. And we have derived something that is combining JSON-LD, which is, I think, well known as a semantic annotation of JSON documents. But we also say we need to have some syntactical definition of a JSON document, which is covered by JSON schema as an industry standard. And if you combine them, we get a lot of features. One is that if a schema is much easier to be transported in a human interface, like having, for example, a form that is rendered based on the schema, because it's not endless. It has a certain limit, which makes sense for a specific perspective on data. And that's what the user expects, because he cannot just navigate arbitrarily deep into a knowledge graph. But it can also derive Python bindings or API, open API specifications from the same schema. And very important, if LLMs are forced to produce structured output, that means not pleasing the LLM to create JSON or RDF, but saying you are forced to create JSON that is compliant, you will do JSON schema as language to do so. So that's a really important connection. And if we decorate our schema with our context, we are also able to consume and produce RDF with LLMs and actually build knowledge graphs, not by RDF editing, but by more human-friendly and even AI-driven approaches. Okay, and this is just a very glimpse look. Just assuming if we have a very sketchy ontology of a data service, then you could define a workflow like, okay, this script here can consume this kind of data asset, producing this kind of data asset. But actually, these are not just semantic terms, but you have actually program code binding like a class, which is the input and the output. And you can write a Python function that says, I do that job. I can do this workflow. And if you're exposing this interface, you can actually call it as a executable microservice that does a certain scientific transformation, but it's also completely RDF annotated by referring to concepts that are not defined only in the program code, in the Python code, but also in the proper ontology in a knowledge graph that is queryable. And this is makes it clear what the connection between semantic web and software engineering provides us in terms of having a scalable, reproducible, maintainable infrastructure of scientific data, but also data services. Yeah, I mean, there's a short video. I guess not really much time for it, but of course, the question may arise if you now have LLMs, why even spend time on doing proper research data management? And in this demo, we kind of showed what is actually possible if you have a knowledge graph. So the research question behind this prototype was assuming we have a knowledge graph that you have all this UI, but the UI is complex. So if you have an LLM that can control also the UI elements and know where you were, you can have a chat, and the chat assists you in finding the right schema to document your experimental result. And you just, throw in, you drop and drag your research data, and the LM guides you through the process of documenting it properly. It's the first step. The next step is, of course, to searching for existing research data, and then you will ask what similar data sets, what tensile test data sets are available in the platform. And then you run an interactive session with an LLM that has full access to your research data management, but also is able, for example, to execute Python code, to run visualizations and plotting complex data like this tensile test in multiple perspectives, zooming, fitting in the graph, etc., etc. So the point here is actually the LM can do quite a lot. So this is a single data set, and there's barely any metadata. It's just a CSV file, and LM can produce, I would say, a paper-ready figure from it without any semantics on top. But to do the same job for 1,000 data sets would be extremely costly to with LM. So LMs are quite capable to do a quick exploration of unknown data, and especially if you're guided by human, but they scale poorly. So do this on all material science publications in the last year would not be feasible, even with a lot of money. Okay, and at the end, of course, LMs are a really important aspect in orchestrating research workflows. That does not mean to handle everything to them, but making use of their intrinsic understanding of scientific problems in optimizing, for example, experiments, but also give them access to a persistent knowledge layer that is also accessible for humans. And I think that's a nice connection point. This knowledge graph that is built on proper semantics is a great knowledge store for humans working in a team. That's also a great knowledge store for LLM that can retrieval and update information from the same source of truth. And I think this is a mission where we need to work together to make this actually happening. And even a Claude Code is currently just using a markdown file as a memory. So this is low tech in comparison, and I think we have better solutions, in particular in Europe. Okay, so just a quick glimpse. So if you look at all standards we want to connect in Materials Commons, there's quite a palette here. But it also shows that there are many existing standards that, deliver solutions for problems we have, from something in deep integration of data spaces up to actually interfaces for human operators. Yeah, and I want to conclude with the missions. I want to point out that we all know that there are very motivated research data management people like me, people like many in the room, and also people that take part in the survey. But it's more like doing this job. So you put something together and somehow works. But it's far away from a reproducible software innovation cycle. And actually, if you look at software industry, there's a clear and proper way to do software in versioning the code, testing the code properly, containerizing the code with all dependencies, make quality checks before you deliver it to a user. And this is what we also would expect from a digital materials infrastructure in the future. Also, if you look at laboratories, there are many excellent laboratories across Europe, which do not have any proper way to be integrated by having actual data flows. So we should have this adoption of the industrial data space concepts. So you are able to expose local resources like your local data repository, your local workflows or service offerings, ELNs, and connect to whatever is of interest for you. It could be, of course, the Materials Commons node. You just want to advertise, so want to disseminate the results. So why not making them visible in a larger catalog? I mean, this would be a great way to say, hey, there's a domain ontology. Hey, there's a new workflow. And it's now findable easily in Materials Commons. But it could also be a national node or a partner node that replicates the similar structure. And of course, we also want to have on board the European infrastructure like EOSC that should somehow follow the same patterns, we hope, as we plan. And this plan to make everything working, so this is actually the data space protocol from the International Data Space Association, and is already a standard draft. And it exactly answers the question, how could we start with something like cataloging in a DCAT AP flavored manner, but going down to actual data transfer that is really bound to trust, to verification of access rights. So we can not even have this public scientific academic knowledge graph where everything is open, but can really go into proprietary and private data sharing without need to find another solution for this way. So there's a proper standard to do it. The only issue is that we need to make material scientists able to operate with the standard, which is complex, of course. Yeah, and that's the final aspect. So the human user is someone who wants to have a single point of access, and there's a lot of software standard components also reinvented in many projects, like having single sign-on, having a somewhat catalog of resources, and then having different microservices that offering, plot this data, answer these questions on a knowledge graph, connecting LLMs, then all this infrastructure like Kubernetes cluster, Docker stacks, down to the actual computer resources. So this stack is replicated very oftenly, but at the end, material scientists only want to operate in a specific adopted application layer on top of this all, and they don't want to go down in the basement and check if there's a cable missing on the server, is there outdated Python version somewhere. So that's what we should take care of so others don't. Yeah, and that's my conclusion. So, of course, happy to discuss how to make this materials commons edition actually work and integrate other projects, initiatives. Thank you.